Hello. Thank you for the invitation to attend, and I will talk about some of the new requirements for composites in some of the new industries, advanced air mobility, unmanned aerial vehicles that are looking at manufacturing these in much higher rates than the aerospace industry is accustomed to. And so I'll talk about kind of where things are today, and then some of the material systems that we're developing and some of the developments happening in the industry that can help enable this high rate manufacturing. Okay. This one? Yep. So first of all, just a brief introduction to HEXCEL. If you don't know of the company, we've been in the industry. We're now celebrating our 75th anniversary as a company. And we're a publicly traded company that is the largest supplier of composite materials to the aerospace industry and the second largest provider of composite materials overall. You can see the split out of our business, about 60% in commercial aerospace, about 30% in space and defense, and then a little bit of industrial. We're projecting revenues of $1.7 billion US this year. In terms of the products that we produce, we're primarily a material supplier, but we do get a little bit into the structures side of the business so that we really can go all the way from raw materials to finish structure. So we, in the upper left, you can see we make carbon fiber that starts off as a polyacrylic nitrile yarn that is then carbonized and turned into carbon fiber. Then we do weaving. We weave our own fiber, but we also weave glass fiber and fiber from other competitors, and can produce a variety of woven fabrics. Then we produce our own resin chemistry for the matrix system, and then develop prepregs that can be unidirectional prepregs or fabric prepregs. And again, some of the prepregs we produce are with non-HEXCEL fiber. We are the largest global supplier of honeycomb material, and that's actually the start where HEXCEL started as a company. So we produce both metallic and non-metallic honeycomb. And then we do engineered structures. So we do work on things like composite rotor blades, spacecraft fairings, and then we have two engineered core facilities that take our honeycomb core and then shape it, form it, splice it to produce the finished structure. So the image in the bottom middle is the 747 engine nacelle, and you can see a variety of densities of honeycomb core on that are shaped and formed and spliced, and then a composite skin will be applied to that. And then we do industrial prepregs. Much of the prepregging for the industrial business is with non-HEXCEL fiber, so we're procuring fiber from other sources, lower cost sources, and then producing prepregs for things like sporting goods, wind turbine blades, and some automotive applications. So when you look at, I'm going to primarily focus on two emerging industries. One is advanced air mobility or urban air mobility. A lot of investment in this area today, a lot of activity, a lot of companies, some here in Korea, some scattered throughout the world that are trying to develop the next generation of urban transport, where rather than getting into a taxi or a limousine to get from point A to point B, you would get in a vertical takeoff and landing vehicle that could take you point to point in much faster, but at a similar cost point as what you would pay for with ground transportation. And then UAV industry, there's a lot of military applications as well as commercial applications for this, and we're just seeing an explosion in the growth of UAVs. But for all these systems, both with UAVs and air mobility, most of the airframe will be carbon fiber composite material. It's needed because the lighter weight the vehicle, the longer range, or the more payload that it can carry. So when you look at a UAV, the wings, the fuselage, the radome, the winglets, pretty much all of the primary structure is going to be composite materials. So what it means for our industry is that, you know, there's going to be a large demand for supply of materials for these new applications, but it also means the supply chain is going to need to ramp in order to be able to meet those requirements. So one of the things that we see with both of these industries is that they are going to go to higher build rates. So if you look at commercial aviation today, you might get up to 70 or 80 ship sets per month when you look at like 737 MAX and the A320. But both of these industries are projecting build rates that will get into the hundreds of vehicles per month. And so that means, you know, material suppliers like ourselves are going to need to ramp to build those, but it also means the companies that are building the structures also need to ramp their capabilities in order to be able to meet the high rate. So you're going to have a higher build rates, but both these industries are also pretty cost sensitive, so they want lower cost. That's lower cost materials and lower cost manufacturing methods to do that, but they still need to maintain that aerospace grade and quality that we've been accustomed to for composites in aviation. Then there's a number of trade studies that need to occur as companies are selecting the material and the manufacturing process. So this can all be dependent on things like part size, complexity of the part. Are you going to automate the process, like using an automated tape laying machine for this? What kind of equipment are you going to need to be able to produce that in those kind of volumes? What kind of performance? What's the quality, technology, maintenance, and so forth? And then you're going to go and select the manufacturing method. So you might use some additive manufacturing, you might use automated placement. We're seeing a lot of interest in resin transfer molding, and I'll talk more about that later. Compression molding is also, because this industry is probably going to need to go to manufacturing methods that are out of the autoclave in order to meet those kind of rates and so forth. So those are some of the trades that we'll do. So I'll talk about kind of where the current state is on some of these and also where the future direction is going. So one of the approaches that we're taking is that, you know, HEXCEL, as mentioned, we're a 75-year-old company. We have lots of our materials that are flying and have been flying for decades out there. And so we're looking at some of these aerospace-grade prepreg systems and finding out, can we be able to manufacture and process them more quickly than we have in the past? And I'll show one example of that. So how can we take aerospace prepregs and find a faster manufacturing method? The other approach is we have these automotive and industrial prepregs that we've developed that generally don't have the performance required for aerospace, but they generally have the fast manufacturing, fast curing aspect. So what could we do with those material systems to increase the performance? And so we're really looking at this high rate manufacturing capability from two angles. We also, if you look at aerospace today, it's predominantly using prepreg, okay? That's what the industry's familiar with. But resin infusion has been around for some time, we're seeing a lot more interest both from just commercial aerospace, because it has the aspect of decreasing manufacturing cost and increasing rate. But we're seeing a lot of interest from the UAV and AAM spaces in using infusion, especially for the rotor blades, but we see applications for the airframe with infusion, and so I'll talk some more about that. Okay, so let's talk about the standard cure systems. So when you talk about advanced air mobility, nobody has certified an advanced air mobility vehicle, although I guess EHang has just certified in China. Okay, so that's the first vehicle that's been certified, but no vehicle has been certified from either the FAA or EASA to do this. So in order to reduce risk, we're seeing a lot of the early companies wanting to go after standard material systems, autoclave cured, ones that have a pedigree and a history with the certification agencies, because they see this as the lowest risk approach to certification. And obviously this whole business segment doesn't exist without certified vehicles. So we're seeing this movement towards traditional materials today, but then a look towards version 2 of the vehicle to be with a higher rate material system that can be cured out of the autoclave with automation. So that's the current framework that we see. So when you look at, and Royal just gave you a good summary of the capabilities at NIAR and NCAMP, this is required to get certified vehicles. And so we're already seeing a movement of companies, and HEXCEL's included, to start getting in the certification or the qualification timeline these higher rate material systems that will, so that data will be available when the industry is moving to version 2 vehicles, where they will want to use some of these newer material systems. And so it's very important that, you know, as the NCAMP process can take 18 to 24 months, so this industry wants to move fast, and so there's a lot of activity around being able to get these newer material systems qualified so that they're ready when the industry's ready to move. So I'll just talk about one of these material systems that is currently flying today that is of interest to this industry for the initial certification vehicles. So this is our M21E matrix system with an IMA fiber. This is currently the primary structure material for the Airbus A350. We are planning an NCAMP qualification with this material, so data will be publicly available on this. It has excellent properties, and it has gone through all the certification with Airbus on this vehicle. And so this is the type of material system that the industry is looking at for these initial vehicle builds, because they know that in terms of the material qualification, the data's there, and that the EASA and FAA have experience with the material, and it's performed well for a number of years in industry. One of the ideas that we had, 8552 is another material system, and Royal showed that that is one of the material systems that is in NCAMP today. 8552 has been around for decades and has been flying on both commercial and defense platforms for decades. So one of the things with this move towards high rate, we thought, hey, I wonder if you could compression mold 8552 and how the material properties would stand up under compression molding. So we started this project about a year ago and have a lot of data completed. And actually, with a 30-minute compression molding cure cycle, we're getting equivalent properties. In a couple of cases, properties are actually slightly improved over the autoclave cure system. And so we're completing some of the testing on this, but one of the ideas that we have is to do an equivalency qualification of this system, and this gets you from a 6-hour cure time to 30 minutes. Now, the tooling for compression molding can be pretty expensive, so unless you're getting high rate, it doesn't make economic sense to go this route. But the rates that the UAV and air mobility industries are talking about, this looks really promising, and this is just with one material system, so we could do this with other autoclave cure material systems as well, and that is a way where a supplier would not have to switch material systems to go to high rate. They could start out with an autoclave cure system, and then when the volumes get to high rate, they could switch to compression molding and still get equivalent properties. Okay, but as I mentioned, the move towards the future is for out-of-autoclave systems, and so let me talk about a few of those that we've got. So M56 has been our out-of-autoclave solution for a few decades now. The material system performs well, it's been qualified, it's flying today, and it's a good system. Generally, it's slightly more expensive than the autoclave cure system, but you save the expense of autoclaves, and also the manufacturing is going to be less expensive. And when you compare material properties of M56 to 8552, they're fairly equivalent. You can see, slight up or down between the two systems, but it is a, good aerospace quality system that we've got good experience with. But we've been looking at, newer systems, and so there's some newer systems that will be coming out that we'll be releasing soon as kind of the next generation of out-of-autoclave systems. We get slightly better performance, maybe a little bit better processing capabilities with that. So stay tuned with HEXCEL's roadmap in regards to other material systems coming forward that will be out of autoclave. And then, as I mentioned, we've seen a lot of interest in infusion. So you've got commercial aerospace, you've got Airbus that's been leading the Wing of Tomorrow program, which is an infused structure, but there's a lot of interest in infusion for these new industries. So when you look at, HEXCEL's been in, developing materials for infusion for a number of years. So we have unidirectional tape that is designed for infusion. So it has a thin thermoplastic veil on it that allows you to tack it down and use it with automated equipment. But then it's a dry fiber preform compatible with our infusion resin systems. We have a non-crimp fabric version called HYMAX. Similar, it has that thin thermoplastic veil that allows you to be able to lay it down, but it's dry fiber and then compatible with our high flow resin systems. So up at the top middle is RTM6. So that's been our kind of go-to resin infusion system. Again, been used for decades, well developed, well characterized, well understood by the certification agencies. But we've been active in developing several new infusion resin systems, and I'll talk about a few of those today. But 1078-1, that's actually going through an NCAMP qualification, so that will be public and can be used with a variety of fabrics. RTM 200 is a brand new system that we just introduced this spring. It is a lower temperature cure system. There's been a lot of interest, especially for like rotor blades, in that the lower temperature cure allows for lower cost tooling to be able to use with that, so it can save quite a bit of expense, but has good mechanical properties. Then we have a fast cure system, HF610F2, that has been developed, and then we have a tough resin system, the RTM 250 ST, that just adds some tough lane. Let me talk a little bit about RTM 200 and the HF6110. So if the HF6110, one of the challenges with high-rate resin infusion systems is that the reaction to cure the material can sometimes kick off before you fully infused the structure. And when you talk about large structures, you need time to be able to get the infusion in there before you want to initiate the curing process. So this 610F2, it's got very good viscosity for about 5 minutes for you to do the injection, and then the cure time is about 25 minutes. So a total cure time of 30 minutes from going into the press to getting it out of the press. And so that is going to be able to get up to rates like, as mentioned here, 15,000 parts per year possible. So this is a high rate system that has good mechanical properties. And then the RTM 200, as mentioned, we had gotten a lot of requests from the industry to say, hey, your typical RTM 6 has a 350F cure on this, and that requires us to go to kind of high or very expensive tooling. If we could get down to a 250F cure system, then we could go to lower cost tooling, and that would allow us to really reduce the price and increase the rate. So we came up with the RTM 200. We've had it tested and evaluated at a number of customers with very positive feedback on this. And this really looks like a great material system for the future for both the UAV and advanced air mobility industries, because it will allow the high rate. You can take advantage of infusion, which can lower costs once you amortize the cost of the tooling. But in this case, you can go to lower cost tooling because of the lower cure temperature. So with this, we have a couple of partners in the U.S., and NIAR is a partner on this as well, where we decided let's go and do a preliminary qualification of this material with 2 fiber systems. So Fiber Dynamics, which is a Wichita, Kansas-based company that are experts in infusion, along with AMP, who braids material, and so they braid a lot of the sleeves that are used for the rotor blades. And we've got some partner cash from NIAR on this. So we've initiated this process to be able to do a full qualification of the RTM 200 material system specifically for rotor blades. And so we expect in about a year, we're going to have quite a bit of data available on this that will be that we can share with our customers. So as they look at this new version infusion resin system, being able to get that qualified on an actual component that will be flying. And then I wanted to just touch on a couple of supporting technologies, and then I'll summarize. One of the areas that we've also seen a lot of interest from both of these industries is they want lower aerial weight fabrics. They're very weight sensitive. And so we have pioneered a technology we call PrimeTex, which essentially takes a standard woven fabric but is able to spread the toes so that you get very few gaps in the fabric. And so we can make this in 145 grams per square meter type of configuration. And so this is a material system that is getting, especially for the advanced air mobility market, they tend to be wanting to go with PrimeTex versus a standard woven fabric, as it gives them better mechanical properties and a lower aerial weight material system. And then another system that we introduced recently is really a surface coating material. So we call this M98. And so this, you can take your structure. This is going to be very important for advanced air mobility, because you're going to want the vehicle that you get into to be to look nice and safe. And so this surface coating technology, M98, we've developed. Also, you can see on the far right, it has much better UV light capabilities, resistance. And so these vehicles are going to be outside much of the time, and so having a very good UV-resistant coating is important. So this was just introduced this year. And also, we have demonstrated that you can combine that with a copper foil, so you can add the lightning strike protection with the surface coating all together. And so this is being promoted especially for the advanced air mobility and commercial aviation market, where they need good surface finish, and they need that lightning strike protection, and they need the UV resistance. So in the summary here, when you look at these new industries, so advanced air mobility and the UAV industry, there's a number of steps that companies have to go through in order to be able to deliver that product to the market and have it certified and so forth. And so I just have check marks here that between HEXCEL and the partnerships that we've established, we really can be that end-to-end partner for companies in order to be able to develop the composite structures that are needed for these new industries. And then here's my contact information. Be happy to share some of these slides with you or be able to collaborate with you on additional information that you need. I do lead HEXCEL globally in regards to these two industries, unmanned aerial vehicles and advanced air mobility. So, anywhere in the world I can help support that. So with that, I'll open it up for any questions.
Thank you, Dr. Yancey. Okay, I think we had a great time to understand what's going on in the global leading company. Okay, so you have any questions or comments? Okay.
Excuse me. Thank you. It's a very interesting talk. I'm particularly interested in the 8552 compression molding and driving that cure cycle time down to 30 minutes. Are you, and maybe you can't tell us, but is there a modification of the resin system, or are you changing B staging at all, or?
No. So this was an idea we had, and we thought, okay, well, let's try it out. Not sure what we would get. So we haven't made any modifications. We're using the standard pre-preg that we're developing. Right now, we've only done it with matched metal tooling on a flat plate, right? So I think we still need to do some work on doing it in a curved structure and making sure that there's no issues with that, but no modification. Now we have played around a lot with temperature and pressure to figure out what the right setting is. So I will say that temperature-wise, it is being cured at a higher temperature than we're curing in the autoclave, okay? But we played around a lot with that and kind of honed in on what that process should look like. And like I said, all properties are equivalent except for a few that are has slightly better compression properties than an autoclave cured system.
So do you still reach the same TG baseline for particularly at wet?
We measured TG on this to look at it. I would say the TG is pretty much the same as with the autoclave cure system. But we did look at that as a variable as well.
Yep. All right. Thank you.
Okay, any more questions? Okay, let's give the speaker a big applause again. Okay, thank you.